Hello class, welcome to this video in the calculus series. So we're looking at lesson 5, infinite limits. In the previous lesson, we looked at one-sided limits and defined the notion of continuity. So we're going to continue exploring infinite or discontinuities in the form of infinite discontinuities. So, for example, vertical asymptotes, and we're going to, explore the idea of infinite limits in that discussion. So, what are infinite limits? So first, let's consider this function. We've seen functions like this before, hyperbolas, where they have the vertical asymptote, where the function blows up. So we want to describe this using, calculus or, the idea of limits. So we're going to use one-sided limits in order to explore what's going on either side of this vertical asymptote. So let's start with on the left side. So the limit as x approaches 5 from the left side of the function, notice that as we approach 5 from the left, the function is going down. It's dipping into the negative numbers, right? So it's getting more and more negative. In other words, it's going to negative infinity. If we approach 5 from the right side, notice that the function is going up and it's getting bigger and bigger. So it's approaching positive infinity. So it's behaving differently on either side of 5. So these limits are referred to as infinite limits. As you approach one side, as you approach a value, the function increases or decreases without bounds. So notice that for infinite limits, they actually don't exist. So the above limits do not exist because they don't approach the same single values. So even though we refer to them as positive, negative infinity, remember that infinity is not a number, so these values it's not a single value, and therefore the limit actually does not exist. So another way that we would write that the limit does not exist is with sometimes we write it as DNE. All right, so in other words, you can write the limit as infinity, negative infinity, or you can use does not exist. We'll get more into this in a little bit. So let's look at another example. So in these two functions, notice that if I plug in 1 into the denominator, I get a value of 0, which you know that we cannot divide by 0, and so therefore we have a vertical asymptote at x equals 1. So we want to determine the one-sided limits as x approaches 1, from the left and from the right. So if we plug in a number just to the left of 1, such as 0.9, then we get a value of 100. Notice that if we also tried to plug in x equals 0, which is also to the left of 1, we would get 1 over negative 1 squared, which is 1. So we know that as we get from 0 to 0.9 to 1, well then the function is getting bigger, right? From 1 to 100 and so on. And so the function is approaching positive infinity. Now if we see the behavior from the right side, let's plug in a number such as 1.1. Then in that case we get a value of 100, just like before. If we plug in a value such as x equals 2, which is far away from 1, relatively speaking, we would get 1 over 1 squared, which is 1. So as we get from 2 to 1.1, closer and closer to 1, the function is blowing up, and it's going to positive infinity as well. So on either side, we have infinity. Now for the function on the right, if we're going to do the one-sided limits, this time instead of plugging 0.9 in, which is close to 1, let's plug in a number even closer, 0.99. So if we plug in 0.99, we get a value of 300, which is pretty big, and it's positive, so we're going to say it's positive infinity. Now if we approach 1 from the right, let's plug in a number such as 1.01, it's even closer than 1.1. We get a value of negative 300, so now it's negative. So now not only is infinity, it's negative infinity. All right, so if we look at example A, and we actually graph it, notice that as we approach 1 from the left, the function is going to positive infinity. As we approach 1 from the right, the function is approaching positive infinity. The function is blowing up in the positive side when you approach from either end. So this line is known as the vertical asymptote, right? So we know that this line is a vertical asymptote. So we have vertical asymptote at x equals 1. And we're going to define what a vertical asymptote is in just a second, but we're going to be using the idea of infinite limits in the definition of vertical asymptotes. So speaking of which, let's define what a vertical asymptote is. And we're going to do it with this theorem. So theorem 5.1, vertical asymptotes. Let f and g be continuous functions on an open interval containing c. If f at c, or f of c, does not equal to 0, and g of c is equal to 0, and there exists an open interval containing c such that, again, sometimes we refer to this as such that, right? That's how we refer to it. Containing c such that g of x does not equal to 0 for all x does not equal to 0 in the interval, then the function h of x equals f of x over g of x has a vertical asymptote at x equals c. So g of x is the denominator, and we know that if the denominator is 0, we have a vertical asymptote as long as this does not equal to 0. That's essentially what the theorem is saying. So for a specific value, if that's true, we have a vertical asymptote. Okay. Now, in terms of the limits and stuff, we know that essentially, in other words, if at least one of the side limits increases or decreases without bounds, so another way of defining vertical asymptotes is, as x approaches a value from the left or from the right, and it blows up, it goes to positive infinity, negative infinity, whatever, then we know there has to be a vertical asymptote. All right. Remember that positive infinity, negative infinity, the infinite, limit happens at the when we have that vertical asymptote. All right, so a note on infinite limits. So here's a quick note on how to write the answer for an infinite limit. So if you have two infinite limits, or two one-sided limits rather, and they're both positive infinity, then you can say that the general limit, which is the two-sided limit, is also infinity. You can also say that it's equal to dne or does not exist. Because remember, infinite limits, infinity is not a number, so technically it does not exist for the limit. Now, if you have the two one-sided limits that agree on negative infinity, then you can say that the two-sided limit, just a general limit, is negative infinity or does not exist. And in the final case, if you have a mixed set of limits, whereas one one-sided limit is negative infinity or positive, and then the other one is the opposite, so negative or positive infinity, so they're mixed, then we can say that the general limit or the two-sided limit does not exist. So what you would say is if these are different, right, then you would write dne. There's no other choice in the matter. You just have to say does not exist. You can't say infinity or negative infinity because they don't even agree on whether it's positive or negative, right? It just does not exist. All right, so let's look at an example. So let's find the vertical asymptotes of the following functions. Remember from theorem 5.1, if the denominator is 0 and the numerator is non-zero at a specific value c, then we have a vertical asymptote, right? Assuming we have f and g are continuous functions. When we refer to f and g, we're not referring to this function, right? We're referring to these functions. This is in the theorem. This is f of x and g of x in the actual theorem, right? So just to make sure. But we know that if we on the left side, on the left function, we know that we can, if we factor the bottom, we have a difference of squares, x plus 1, x minus 1. Notice that the x plus 1's cancel, leaving us with 1 over x minus 1. So what that's saying is that when x is negative 1, this starts canceling out, basically. So basically we have a discontinuity at x equals negative 1 because that does make the denominator 0. However, it's removable. So it's not an infinite discontinuity. So it's not a vertical asymptote. However, we do have a non-removable discontinuity at x equals 1, right? That's non-removable. And so we have a vertical asymptote there. All right, so again, so the denominator is equal to 0 when x is negative 1 or 1. However, when you plug in negative 1 into the numerator, you get 0. So that indicates that it's essentially like a removable discontinuity. It's not a, it's not a vertical asymptote. When you plug in 1 into the numerator, you don't get 0, right? You get 2. And so that tells us that, well, the denominator is 0 at 1, but it's not 0 when the numerator is not 0 when x equals 1. So we have a vertical asymptote at x equals 1, but not at x equals negative 1. So it's pretty straightforward just to see if the numerator is non-zero and the denominator is 0. So for the second example, cotangent of x, remember that the identity for cotangent is cosine over sine. So we want to see where the sine is equal to 0, right? Where the denominator is 0, but where the numerator is not 0. So remember that the sine is 0. If we were to draw the function for sine real quick, we know that the function is 0 when x equals 0. And it's also 0 when x is pi, right? So at pi over 2, it goes to 1. So we got 1 here, we got -1, and it just goes like this, right? So it's an oscillating pattern between 1 and -1. And every time it hits an integer of pi, so here this is 2 pi, so when it hits an integer of pi, that's when the sine is 0. And so this is for sine of x. Now if you were to do the same thing for cosine of x, well, we know cosine of x is 1 at 0, at x equals 0. Oops, sorry, I didn't mean to put a point there. Point is here at 1. And then at x equals pi, the function is actually -1, right? And then when we get to 2 pi, the function hits a value of 1. Okay? So we can see that when the sine is 0, the cosine is non-zero, right? So we can say with confidence that, when x is 0, pi, 2 pi, 3 pi, n pi, where n is an integer, so n is an integer. So n could also be negative, because you can have -1 pi, and that would also get you to 0, all right? Same thing with -2 pi, right? So n could be positive or negative. And cosine is non-zero at those same values, and therefore by theorem 5.1 we have a vertical asymptote. There are infinitely many at x equals n times pi. All right, so let's look at another example. So we want to find the one-sided limits. So let's do so we know that x equals 1 is a vertical asymptote. And again, you can do this by actually plugging in 1. So let's verify this. So if we plug in 1, we get 1 squared minus 3 times 1 over 1 minus 1. So we know that the numerator is non-zero, whereas the denominator is 0. Sorry, I should probably be careful with my notation here. So we're going to say for the numerator we get 1 minus 3 is -2, denominator is 0. So the numerator is non-zero, the denominator is 0. So this is a vertical asymptote. So let's look at the one-sided limits. So if I do it from the left side, let's plug in 0.9. We get 18.9 for the value. So that tells me that's positive infinity because it's going to the positive side and it's getting bigger in the positive direction. Now let's do the limit as x approaches 1 from the right. If I do that, like for example 1.1, I get a negative number, -20. So it's blowing up in the negative direction. So it's negative infinity. All right, that takes care of that example. Pretty simple. Now let's look at some properties. So suppose C and L are real numbers, so they're elements of a set of real numbers, and let f and g be functions with the following limits. So the limit of f of x as x approaches c is infinity, and the limit of g of x as x approaches c is a number L. So suppose we have that. Well then, if I were to take the sum or difference, so if I were to add those functions or subtract those functions, and I take the limit as x approaches c, I'm going to get infinity. And the reason is as follows. So we're going to show you. So we know that the limit of a sum or difference is equal to the sum or difference of the limits separately. That's one of the properties we mentioned in the previous lesson. So we can split the limits into 2, essentially. And then we know that the limit here is infinity. And this limit is L, because of what our suppositions here. And we know that infinity plus a number or minus a number is always going to be infinity. Now there's one note that we need to mention here. Suppose we have g of x minus f of x. Well then we know that the limit as x approaches c of g of x is L, right? And we know that L minus infinity is negative infinity. So for example, if I had 5 minus infinity, well that's just negative infinity. All right, because 5 minus a really big number is a really negative number, right? So it's a negative number. So a positive number minus a really big negative number, or really minus a really big number, is a negative number. So hence negative infinity. So now let's focus on the product. So if we take the product of two functions and then try to evaluate the limit, well, we know that since the limit of one of them is L, the limit of the other is infinity. Well, a number times infinity is infinity. As long as the number is positive, right? If the number is negative, like -5 times infinity, well, that's going to be a negative number, so it's going to be negative infinity. So this is the case where L is positive, and this is where L is negative. So again, if L is positive or greater than 0, then when I take the product, I can split the limit into two and then realize that this is infinity and that this is L. And as long as L is a positive number, I get positive infinity. But if I repeat this with L is negative, then I get negative infinity. Positive number times a negative is a negative. All right, so number 3, take the quotient. So L does not necessarily have to be greater than 0. So I'm gonna get rid of this idea that L could be greater than 0. We're just gonna say we have the quotient, and we know that if the denominator is infinity, we're gonna get 0. So if we take the limit of this quotient, notice that we can take the limit separately in the numerator and denominator. And we know that the limit of g of x is L, a number. The limit here is infinity, for the bottom. A number divided by infinity is 0, because if I have, for example, 5 over x, and x is allowed to grow without bound, then, for example, 5 over 10 is 1/2, right? Whereas 5 over 100, x is now growing from 10 to 100, well, it's 0.05. And then if x is allowed to grow further than to 1,000, then we get 0.005. So the number is approaching 0 here, getting smaller and smaller. So a number, regardless of whether it's positive or negative, this can work in the positive or negative. So let's suppose we have a negative numerator. Well, I mean, it's still going to approach 0, okay? So the quotient property, notice that infinity on the denominator is going to give us 0. All right, so let's look at some examples. So determine the following limits. So if I take the first one, let's take the limit as x approaches 0. We can split this into two limits, right? So we can sort of like distribute almost, right? The limit of 1 is just 1, right? So that's pretty straightforward. Now, we know that if we plug in 0 into here, we get 1 over 0 squared, which is undefined, right? So therefore, we have a vertical asymptote there. So we're going to split it into two one-sided limits just to see how it behaves. If I approach it from the left, so if I plug in, for example, negative 0.1, negative 0.1 would work because that's pretty close to 0. So if I plug in, for example, 1 over negative 0.1 squared, right? Well, then that's 1 over 0.01. Well, 1 over 0.01 is 100. And so it's positive infinity. Now, if I approach from the right side and I plug in, for example, x is 0.1, well, I get the same thing. 1 over 0.1 squared is 100, and therefore approaches positive infinity. So on either side, it's infinity. All right, so let me get rid of this annotation. So in this case, we have infinity. So because these two are infinity, that means we could say that the general one-sided limit is infinity. Or we could say it does not exist. So we could say that the answer is infinity or does not exist. Also note that this is infinity, so if we plug this in here, we get infinity. But 1 plus infinity is still infinity. That's one of the properties we mentioned, okay? All right, so let's look at the second one. So for the second one, we note that if I plug in, if I do 1 from the left, let's focus on the numerator first. 1 from the left, I can do a direct substitution here. because, I could do a direct substitution and just makes things a little bit easier. Because we know that this function, x squared plus 1, is continuous everywhere. So there's no tricks that we need to do. We could just do a direct substitution, right? So if you do a direct substitution, we get 2. Now for the denominator, however, there is a potential of a vertical asymptote. So we want to be careful about the one-sided limit here. So we're going to do the one-sided limit. And what we're going to do, we know that cotangent, remember that cotangent of x, we mentioned this earlier, but cotangent of x is undefined when x is equal to n pi, right? Where n is an integer. So at 0, pi, and so on and so forth. So if I plug in 1 into here, well, I'm going to get pi. And so we know that cotangent of pi is undefined, right? So we're going to need to keep this in mind. So when we plug in, we can't do a direct substitution, but we want to get as close to 1 as possible. So let's plug in, for example, 3/4. If we plug in 3/4, that's pretty close to 1, and it's to the left of 1. So let's do cotangent of 3/4 pi. Well, we know cotangent of 3/4 pi is -1, all right? So you can do that on the calculator, or you just use your unit circle, because we know that cotangent is equal to cosine over sine. So in this case, we have cosine of 3 pi over 4 divided by sine of 3 pi over 4. And if you evaluate those, you're going to get -1 when you divide them. All right, so we know that since we got a negative number, has to approach -infinity. And if you think about it, that makes sense, because we know that the cotangent generally behaves like this, right? The cotangent graph essentially looks like this, right? So it has that shape, right? So where at 0 we have a vertical asymptote, and at we know that at pi we have a vertical asymptote, right? So the graph kind of has that shape. Okay, and we know that this graph repeats, right? So there's another one here, and so on and so forth, right? But as we approach, this is let me replace this with a vertical asymptote. So as we approach this from the left, the function is going to -infinity. You can see that the function is going down. As we approach it from the right, the function is going up to +infinity. So this makes sense, right? All right, so in other words, since this is -infinity, we're going to plug it into the denominator and get -infinity. But the numerator, remember, was 2. So a number divided by infinity is 0, according to the properties we mentioned earlier. All right, so let's do part C. So the limit of, as x approaches 0, of 5 cotangent x. Now we know how the cotangent behaves, so we can use that here. We know that the cotangent of 0 is undefined, so we're going to evaluate it at both sides. Again, just refer to this graph. So this is at x equals 0. This is at x equals pi. The function behaves like that, right? Where this is x and this is the y-axis. The y-axis is a vertical asymptote for the function. So we know that, and then we know that, sorry, this is actually the wrong way. It should be going this way. Sorry, what I drew. So that's the cotangent, and we have another repetition like this and like this. But we are only concerned with x equals 0. So as x approaches 0 from the left, the graph is going down. As x approaches 0 from the right, the graph is going up to +infinity. But let's test this out. So let's plug in a number just to the left of 0, such as -pi/4. Okay, that's a negative number to the left of 4, to the left of 0. Well, cotangent of -pi/4, well, that's cosine of -pi/4 divided by sine of -pi/4. But we know that cosine of -pi/4 is simply is a half, right? And oops, not a half. I meant I wrote a half. It's 1 over square root of 2, The cosine of power 4 is 1 over square root of 2. I'm just going to write it as square root of 2 over 2. So my bad. And then the sine of negative power 4 is negative square root of 2 over 2. Just, you can use your unit circle, or you can just plug it in the calculator, get the answer. But if you divide them, you get negative 1, right? And then, so that's negative 1, but then negative 1 times 5 is negative 5. So we get negative infinity. All right? It's just showing you a little bit of the work that goes, when you plug it in. So then if we do it from the right side, we can plug in like power of 4. And again, similarly, we're going to get a value of 1. But then 5 times 1 is 5. And so we know it's going to be positive infinity. And we can see that from the graph. So because we have two directions, one negative, one positive infinity, we're going to write the answer as simply d and e. All right, so let's look at the last one, part D. So we're going to split into two different limits. So essentially sort of, splitting this up, almost like a distributed property, almost. And then we know that this is a polynomial, so we can just do a direct substitution. So 0 squared is just 0. So this is simply 0. But if you plug in 0 into here, we know that that's 1 over 0, which is a vertical asymptote. It's undefined. So again, we're going to need to evaluate it more closely. So let's look at the 1 over x more closely. Let's plug in a number such as negative 1 over 10. Negative 1 over 10 is to the left of 0, right? So let's go ahead and plug that in. Well, if we do that, 1 over negative 1/10 is negative 10. So that's a negative number. So that gives us negative infinity. So on one side, on the left side is negative infinity. All right, and they only wanted us to do the one side, so we don't have to worry about doing from the right, just from the left. Okay, so we can write that it's negative infinity, or we can write d and e. All right, that is it for the lesson, guys. So here are some review problems. So I like as usual, I suggest pausing this part of the video and maybe try a stab at the problems, and then we'll go over the solutions. So here's 1 through 9. 1 through 2, you want to determine the following limits. Number 3, determine whether it has vertical asymptotes, and so on and so forth. So go ahead and practice. Here's another, so here I thought there was another set. So it's just the questions 1 through 9. So let's take a look at the first one. Determine the following limits. So indicate whether the function approaches infinity or negative infinity as x approaches negative 2 from the left and from the right. Okay, so first off, let's do negative 2 from the left side. So let's do the limit as x approaches 2 from the left of 2 times the absolute value of x over x squared minus 4. Now, because we have the absolute value here, what we're going to do is we're going to remind ourselves of what it means to have that as an absolute value, right? So what it means is, well, actually, what we're going to do is instead, just plug it in. But we know that if we do a direct substitution, we get 0 in the denominator and negative on the numerator. So if we try plugging it in, we know that we're going to get a 0 in the denominator. So what we're going to do is, since we're doing it from the left side, let's plug in a number just to the left of that. So let's plug in a number such as 1.9, right? So if we do, okay, sorry, I didn't mean to zoom in that far. So if we plug in a number such as 1.9, so let's plug in x equals 1.9. So we get absolute value of 1.9 over 1.9 squared minus 4. All right, and really, it doesn't really matter what this number is, because we know that all we want to know is whether it's positive infinity or negative infinity. So we only want to know if it's a positive number or a negative number, right? And I forgot there's a 2 here, right? There's a 2 in front of right there. So all we want to do is know is it positive or negative, and that'll tell us whether it's positive infinity or negative infinity. So since we have an absolute value, that indicates that we're always going to have a positive number. So I'm just going to say that this is a positive number. So I'm just going to say it's a positive number. And that indicates it's positive infinity, okay? So we're going to say that this one-sided limit is positive infinity. Now, if we do the limit as x approaches 2 from the right, of course you could plug it in the calculator and get a number. But remember, we're only concerned, we know it's going to be infinity or negative infinity. We just have to determine what direction it's in. So now let's plug in one number from the right, like 2.1. Well, again, similarly, if we plug in 2.1, we get 2.1 over 2.1 squared minus 4. And this is going to be a positive number because we have the absolute value. And therefore, has to be positive infinity. All right. And then therefore, they're not asking for this, but if they were to ask you for the general two-sided limit, you would just say that the general two-sided limit, just the regular limit here, is infinity or does not exist. Okay. All right. So let's take a look at number 2. So we're doing the same thing as x approaches negative 2, however, whereas before it was, so this time we're doing negative 2. So the limit as x approaches negative 2 of the function, 1 over x plus 2. So we know if we plug in negative 2 into here, if we do a direct substitution, we're going to get 0. So we know it's a vertical asymptote, and therefore we want to see, let's plug in a number just to the left. So let's plug in, for example, negative, just to the left of negative 2 is negative 2.1, right? So let's do from the left side. So let's see, if I plug in negative 2.1 into here, I get 1 over negative 0.1. And 1 over negative 0.1 is negative 10. So it's a negative number. So we have negative infinity for the limit from the left side. The limit as x approaches negative 2 from the right side. So again, if we plug in, for example, x is equal to a number just to the right of negative 2, so such as negative 1.9. Remember, negative 1.9 is just to the right of negative 2 on the number line. Then we get net 1 over negative 1.9 plus 2, which is 1 over 0.1, which is 10. So we get positive 10 this time. We get a positive number, and therefore we get positive infinity. Again, the number here is not really important. It's whether it's positive or negative. That's really what we want to determine the direction of infinity, right? Positive or negative. So in this case, if we were to write the one-sided limit or the two-sided general limit, we would write D and E because we have two different directions. All right, so on number 3, determine whether the function has vertical asymptotes or removable discontinuities. All right, so in this case, remember, we want the denominator to be equal to 0, so we're going to set this denominator equal to 0, right? Oops, let me went a little bit too far there. So let's see, we have x squared plus 9 equals 0. So set the denominator 0. Well, if we do this, well, we know that there is no number. If we try solving this, right? If we subtract 9 on both sides and try solving it, and try taking the square root, well, we can't take the square root of a negative number in the real numbers, right? The solution is complex. It's a complex number, or two complex numbers. So we're going to say that there is no solution in the real numbers, right? So in that case, we're going to say that there are no vertical asymptotes, okay? So we're going to say that for this equation, x has no solution, right? So x has no solution in the real numbers, right? Therefore, that's a symbol for therefore. There are no vertical asymptotes. All right, so no vertical asymptotes and no removable discontinuities. for this one. All right, so number 4, again, just look at the denominator and see where that's 0. But also we have to consider that the numerator cannot be 0, right? So in this case, we're going to see about factoring the denominator, because if we can cancel out a common factor for the numerator and denominator, that's going to be where they're both going to be 0. So if we cancel that out, we can get rid of any removable discontinuities. Okay, so first we are going to see about factoring the numerator, which is pretty straightforward. Just pull out the 4. In that case, we get x squared plus x minus 6. We can also factor that further, which we'll do in just a second. For the denominator, let's go ahead and factor by grouping. So I'm going to write it like this. So here we can pull out an x to the third power. So I get x minus 2. And then here we can pull out a negative 9. So we got a negative 9 times, we can also pull out an x, I forgot. So we can pull out an x. So we get negative 9x times x minus 2. So there we go. And for the numerator, we can factor out the numerator. I always like to do an x table. So we got the factors of negative 6 to add up to 1, which are 3 and negative 2. So this is x plus 3 times x minus 2 over, and then for this we can factor, so we can factor it as follows: x cubed minus 9x times the common factor x minus 2. All right. And we can also pull out an x here, so that's what we're going to do next. So we're going to pull out an x there. So we get 4 times x plus 3 times x minus 2 over, on the denominator, x times x minus 3, or x squared minus 3, or minus 9, sorry, times x minus 2. And again, we can factor out x squared minus 9 further, right? So we can factor that even further, because this is a difference of squares. So we can factor it into x plus 3, x minus 3. In other words, if you were to do the table here, it would be negative 9 and 0, which would be positive 3 and negative 3. All right, so 4 times x plus 3 times x minus 2 over x times x plus 3 times x minus 3 times x minus 2. All right, there's a lot of factoring in this one. So we can cancel out the x minus 2. So we got a removable discontinuity there. So we're going to list those out. Removable at x equals 2. So if I plug in x equals 2, or yeah, that's going to cancel out there. And then notice that x plus 3, that's removable as well. So at x equals negative 3, because that's when this is 0, right? This is 0 when x is negative 3. All right, so we are left with 4 over x times x minus 3. So in this case, we have two non-removable discontinuities, right? Non-removable. In fact, they're infinite discontinuities, right? They're vertical asymptotes. At x equals 0, if I plug in 0 there, and x equals 3, that makes that 0. All right, so that's removable and non-removable. All right, hopefully that makes sense. There's a lot of factoring involved, so if you might want to refresh up on factoring if need be. All right, so number 5, we got g of t is equal to t over sine of t. So again, so the vertical asymptote is when the denominator is 0. So let's go ahead and set that equal to 0. But we know that sine of t is equal to 0 when t is 0, pi, 2 pi, and so on. So when t is n pi, where n is an integer. Okay? So we know that we have an infinite amount of discontinuities here. However, we know that the numerator is 0. We know that if I plug in 0 into the numerator, I get 0, right? So note that at t equals 0, we have that the function g of 0 is equal to 0 over sine of 0, right? We know sine of 0 is 0, but then obviously the numerator is 0. So that's telling us that at 0, we do not have a vertical asymptote, right? Because the numerator is 0, okay? So for this, we have no vertical asymptote at x equals 0, okay? And again, that's because the numerator is 0. If the numerator has to be non-zero. However, at any other value, we have a vertical asymptote, okay? So we have, in this case, we're going to modify this and say that the vertical asymptote is when t is equal to n pi for n is an integer other than, and we're going to get rid of the 0. So other than 0. So basically it's a set of all integers except for 0. We're just going to say that. Okay? Or in other words, we could say that where n does not equal to 0, right? We can say that n is in the set of all integers such that n does not equal to 0. There's different ways to say it, right? But in any case, we're just saying that n cannot be 0. Okay? All right. Oh, so usually we don't write so we're gonna, sorry, I wrote the wrong notation incorrectly. It's a set of all n, rather, sorry, the set of all n such that n does not equal to 0 and n is an integer. Okay, n is an integer, but n cannot be 0. All right, so as long as you specify that, you should be fine. All right, so in other words, we have negative 2 pi, negative pi, pi, 2 pi, ... all those numbers. So infinite amount. And we have a removable discontinuity at t equals 0. Okay. All right, so that takes care of number 5. So, all right, so number 6, we have h of theta equals tangent of theta over theta. So so first let's look at, well, obviously, if we plug in 0 into the denominator, we're gonna get 0, right? But we also want to keep in mind so we also want to keep in mind for tangent is consists of sine over cosine. So what we're going to do, what we're going to do for this is we're going to write this as sine over cosine, right? Tangent is sine over cosine over theta. But then remember, we can just divide this. We'll just bring the cosine down. So sine theta over theta cosine theta. Okay? And that just simplifies it further. All right, so now we have, our new denominator is theta cosine theta. So when theta is 0, obviously you're going to get 0 in the denominator. Also, when theta is equal to, so cosine is 0 when the angle is equal to pi over 2, 3 pi over 2, so on and so forth. And so on and so forth. So there's an infinite amount, right? So in other words, if you think about it, another way we can write it is that theta, when theta is equal to n plus a half times pi, where n is an integer. Okay, so for example, if n is 0, you got pi over 2. If n is 1, you have 3 pi over 2. If n is negative 1, we got negative pi over 2, and so on and so forth. Okay, so we got two, sets here. Now, keep in mind that sine, the numerator, sine of theta, is 0 when theta is 0, and as well as pi, or not pi, yeah, pi, sorry, pi, 2 pi, and so on. So because these are both 0, that means at theta equals 0, you do not have a vertical asymptote because the numerator is also 0, okay? Numerator and denominator cannot both be 0 for vertical asymptotes, okay? So here we got removable discontinuity. We have a removable at theta equals 0, because that's when sine and cosine are, or sine, or that's what the numerator and denominator are both 0. And we have a vertical asymptote at, and then in all of these numbers, you have a vertical asymptote. Because if you plug these into sine, you won't get any negative, you won't get any zeros, right? So for example, at sine of pi over 2, you get 1. Same thing with sine of 3 pi over 2. You get -1, and so on and so forth. All right, so vertical asymptote at x equals, or theta, sorry, at theta equals n plus 1/2 pi, where n is an integer. All right. All right, so number 7, find the one-sided limit if it exists. So we're just gonna, so if we plug in 2, we know that we're gonna get 0 on the denominator, right? So that means that we're gonna just plug in just to the left of 2. So let's plug in, for example, 1.9 and see what we get. So 1.9 over 1.9 minus 2, we get 1.9 over negative 0.1, and it doesn't really matter. This is negative, but we know we'll get negative 19. But again, the number, the actual quotient does not matter. We just the sign of the quotient. So in this case, the sign is negative. So therefore, this is negative infinity. All right, and we're done for that. Pretty straightforward. All right, here we're going to see that x approaches negative 1/2 from the right. So first, since we're doing it from the right, let's plug in a number just to the right of negative 1/2. So let's plug in 0. Okay, 0 is to the right of 1/2, and it's not too far away from negative 1/2, right? So let's plug in 0 and see what we get. So if you plug in 0, we get 6 times 0 squared plus 0 minus 1 over 4 times 0 squared minus 4 times 0 minus 3. So we get 0 plus 0 minus 1 is negative 1. We get 0 minus 0 minus 3 is negative 3. Okay, so we got negative 1 over negative 3, which is positive 1/3. Again, the sign doesn't really matter. It just matters whether it's positive or negative, and we can see that it's a positive number. So we can see it's got to be positive infinity, right? First things first, I want to make sure that if we plug this in, we actually get 0 for the denominator, because if we get 0 for the denominator, that indicates it's a vertical asymptote. Again, we want to check just to be sure before we come to any conclusions. So I should have done that first. So let's plug that in. So 4 times negative 1/2 squared minus 4 times negative 1/2 minus 3. So 4 times negative 1/2 squared. So 4 times 1/4 plus 2 minus 3. So this is actually 0. So we do get 0 for this. 1 plus 2 minus 3. If we plug it in to the numerator, let's plug it into the numerator just to be safe. 6 times 1/2 squared, or negative 1/2 squared rather, plus 6 times, or plus negative 1/2, so minus 1/2 minus 1. So 6 times 1/4 minus 1/2 minus 1. So that's 3/4, or 6/4, which is 3/2 minus 1/2 minus 1. So that's going to give us 3 minus 1 is 2, 2 over 2 minus 1. So here in this case we get 1 minus 1 is 0. So that indicates, so maybe we should have actually checked that first, right? So if we plug it in here, we get 0 for the numerator and denominator. So that indicates that we actually have a removable discontinuity here. So what we're going to do is we're going to see if we can cancel it out. So instead of doing all this, so you can scratch this off, let's erase this. So this is what happens when you try to move forward with the conclusion too quickly. So first, we check this and we can see, oh, numerator and denominator are 0. So that means that we don't have infinity or negative infinity or anything like that. We have something that is an indeterminate form, and so we're going to need to figure out what that is. So that usually means that we can, cancel out a common factor or something like that. So let's see if we can factor numerator and denominator. So let's factor 6x squared plus x minus 1. Okay, I'm going to factor this using the AC method. So 6 times negative 1 is negative 6. I'm going to put that in my table. You can factor this however way you want. This is just how I factor it. I set up an X table for the AC method. So I need numbers that multiply to negative 6 but add up to 1. And that's going to be positive 3 and negative 2. And then I'm going to split this into 6x squared plus 3x minus 2x, using those two numbers here, of course, minus 1. All right. I'm not going to get into too many details on this. Factor however you like, but this is how I'm going to do it. I'm going to factor by grouping here. So I'm going to pull out the 3x there. So we got 3x times x plus 1. I'm going to pull out the negative 1 here. So negative 1 times 2x plus 1. And, let's see here. This should be a 2x here, not an x. Okay, so I almost made that mistake there. All right, so then these match. So if these match, we can go ahead and proceed with the factoring. 3x minus 1 times 2x plus 1, using, of course, these two lumped into one factor. All right, so we can factor the numerator as follows, right? So now we're going to factor the denominator. Let's put this off to the side. So let's factor 4x squared. So for this, I'm going to multiply this. 4 times negative 3 is negative 12. So I need factors of negative 12 that add up to negative 4. Well, that is going to be 6, negative 6, and positive 2. All right, so I'm going to split that. So let me rewrite the denominator. I'm going to rewrite that as 4x squared minus 6x, using the numbers that I have from the table, plus 2x minus 3. Going to factor by grouping. I can pull out a 2x there. So we got 2x times x minus 3. And then I can pull out an invisible 1, and we get 2x minus 3. So if I factor it, I get 2x plus 1 times 2x minus 3. All right, so now we're going to lump these into one fraction. All right, so now I'm going to erase this and just replace this with what we have. So this is 3x minus 1, 2x plus 1. If I erase this, that is 2x plus 1 times 2x minus 3. All right, so now we got them. So now let's plug them into the limit. So the limit as x approaches negative 1/2 from the right is 3x minus 1 times 2x plus 1, using the factor form now, over 2x plus 1 times 2x minus 3. So now we factored it, and lo and behold, we have a common factor that we can cancel out. And that's why we got the 0 out of 0. All right, so now we can go ahead and do the limit. Let's do a direct substitution, because now we can do a direct substitution because we eliminated the thing that gave us 0 out of 0. So we can plug in right away. So we got 3 times negative 1/2 minus 1 over 2 times negative 1/2 minus 3. All right, so then plug it in, get your answer. So we got negative 3/2. Let me get rid of this here just to have make enough room. All right, so we got negative 3/2 minus 1 over negative 1 minus 3. So we get negative 5/2, just combining the numerator there, over negative 4. All right, so in that case, that's negative 5 eighths. So if I did that math correctly, please, if I didn't, please correct me in the comments. But I did that. I believe I did that correctly. Okay, so that takes care of the limit. So again, if you try plugging in numerator and denominator, if you get indeterminate form, try canceling out. If you do not get indeterminate form and you get a 0 on the denominator, then do what I was doing earlier, where you plug in a number to the right of -1/2, depending on the direction, and then get your infinity or negative infinity. All right, so let's look at another example, because I know that those polynomials can be kind of tricky with factoring and all that. So now for this one, again, let's try plugging it in, just because I made that mistake earlier. So let's plug in pi. So if I plug in pi, I get square root of pi over cosecant of pi. All right, the numerator is non-zero. So this numerator is not 0. However, the denominator is going to be so remember cosecant, let's recall what cosecant is. Cosecant is 1 over sine, right? So so then what that means is that if sine is, so if not cosecant, sorry, not cosecant. Cosecant is not 0. Cosecant is undefined. That's what I was trying to say. So cosecant itself is undefined because of this. So cosecant is 1 over sine, right? So if I try plugging in, pi into there, okay. So we're going to attack this problem actually in a couple different ways. So first we're going to, attack it with the fact that, cosecant is 1 over sine. So let's do that first, and then we'll show you a different way, which also makes sense, which you'll probably think of doing first. But let's try it. So let's first think of cosecant as 1 over sine of x, right? Well, in that case, we know that the numerator is perfectly fine. We don't no issues with the numerator. It's the denominator we have issues with. So let's do let's focus on the denominator. So the limit as x approaches pi from the right side of cosecant. Oops, sorry. Let's see here. Cosecant of x. So we get, all right, so then if we're going to need to plug into the left side. So let's plug in a number just to the left of pi. Let's see here. For example, we can plug in, sorry, I said to the left, I meant to the right because we're doing plus. So let's plug in like 3 pi over 2, okay? So if we plug in x equals 3 pi over 2, we get cosecant of 3 pi over 2 is 1 over sine 3 pi over 2. And sine of 3 pi over 2 is -1. So this is going to be -1, right? Oh, so it's a negative number, right? So because it's a negative number, it's going to approach, in this case, negative infinity. So in that case, we got, since it's negative, it's going to approach, it's going to be negative infinity. So this equals negative infinity. All right, so remember that the cosecant, if we were to graph it, the cosecant looks like this. Remember the sine looks like this, right? We're at pi, sine is 0. Well, for cosecant, when sine is 0, the function's undefined. So we got basically vertical asymptotes. So then the graph looks like this. So something like that. So it makes sense that when x approaches pi from the right side, we're approaching negative infinity. The function is going down. So that makes sense from the graph. So I just wanted to make sure I share that with you. So, so since this is negative infinity, we get this is square root of pi over negative infinity. But remember, a positive number, any number divided by infinity, whether it's positive or negative infinity, is 0. So therefore, the limit is 0. That's one way to do it in terms of the concepts that we discussed earlier. However, the other way to do it is just simply write cosecant as 1 over sine, right? And then just simplify it. So if I replace this and I write this as 1 over sine, then I can just rewrite this as sine of x times square root of x, right? So I can just say, I can flip the sign up to the numerator. I get square root of x times sine of x. Then if I plug in pi into it, I can do a direct substitution. And we know that sine of pi is 0, and so square root of pi times 0 is 0. So in any case, you're going to get the answer 0, but here I just wanted to show you in terms of infinite limits, you're going to get the same result. Okay? All right, guys, that's going to do it for the lesson. I hope you found this video useful and informative. As usual, I'll see you in the next one.